Thank you, Yogesh. So today I will present the second talk on complex, excuse me, on complex stochastic models and their applications. And today we will talk about learning under group symmetries. So what is the problem of learning under group symmetries? So before stating the problem in concrete terms, let us look at a motivating example. So this is the problem of cryo electron microscopy, and this is a procedure to determine the structure of complex biological molecules, which was awarded the 2017 Nobel Prize. It was developed by these three gentlemen, Duboche, Frank, and Henderson. And the quote here is from the Nobel Prize citation of 2017, which says that these gentlemen have been awarded the Nobel Prize in chemistry for developing cryo-EM for determining the high resolution structure of biomolecules in solution. What is the issue? What is the model? What is the procedure? So it's an imaging technique for the high resolution structure determination of molecules, and and each measurement in this procedure consists of a noisy image of an unknown molecule, and at every measurement the molecule is rotated by an unknown rotation in the orthogonal group in 3 dimensions, and the task is then to reconstruct the molecular density from many such measurements. So basically there are two fundamental challenges in this problem. The first one is this noisy part, so the level of noise is very high. And secondly is the presence of this unknown rotation, which actually introduces a very defining conceptual difficulty in this problem. And the origin of this unknown rotation is actually, lies in the procedure itself, because generally speaking, if your instrument is able to go down to the level of a single molecule or a few molecules, then usually the energy transported by your measurement procedure is usually enough to sort of distort the orientation of the molecule whose image you are taking. And this distortion is usually beyond your control. So you can take as many measurements of your molecule as you want, but usually there will be images of the molecule from different orientations, and you have to aggregate them to produce or try to estimate the actual molecule of interest. This reconstruction problem in cryo electron microscopy has received significant attention from the computational perspective. So there are many computational algorithms to try to process the data obtained from cryo electron microscopy experiments, and try to estimate the actual object. Most of those computational methods are without any mathematical guarantees, and by and large the statistical properties of this cryo electron microscopy model remain largely unexplored. So this is one of the areas where there are more unknowns than there are knowns, and basically if you ask any natural question, it will probably fall in a territory which has not been taken up for research, at least in theoretical terms. So as we already alluded to, it has 2 key features as a stochastic model. So the first one and the defining one is a latent group action in each observation, and in this case it is a rotation. And the genesis of this rotation we have already discussed briefly. So it originates from the measurement procedure in the cryo-EM experiment, and the presence of extremely high levels of noise. And this is also another natural consequence of the of the cryo-EM procedure, because essentially you are zooming down to the level, to a very fine-grained level of maybe a few molecules, and at a cartoon level we might compare it to let's say taking images with our phone camera, and we all know that as we zoom in harder and harder, the grainier and noisier the image gets, and more or less a similar effect happens here. So these two are extremely crucial aspects of this model, and a major part of what we are going to discuss today is to sort of harness these two difficulties. So just to sort of give an idea of how the latent group action can create complications even at a conceptual level. So let us think of a situation where the group action was not present. So what would our procedure look like? So maybe there is an object X, so maybe like big. There is an object X, and there is some noise Y, noise Xi. Let's say it's Gaussian and independent of everything, and I measure X with the noise. So I take many measurements, I equal to 1, 2, 3, 4 up to n. And then the natural statistical procedure, usually it involves taking the average in some sense. And the idea is that, X is the object, so let me call it theta for notational consistency with letter. So if you take the average of all these yi, then usually the idea is that this will give you theta plus the average of the noise. But if the noise is not too bad and means 0, this is going to be a vanishing contribution as n becomes large, and you are going to get xi. So it doesn't matter what the level of the noise is. As soon, so for example, if xi is of variance 1, you can put in a sigma. Sigma is the noise level, and it doesn't really matter. Even if sigma is very high, this procedure is going to work for you. So the size of this term will be roughly of the order sigma over root n. So basically, to beat this, you have to take n to be bigger than of the order sigma square, right? So this is the classical statistical setting. The problem is that now suppose you have these rotations. So then what happens is that, so let us take a simple example. So suppose you have a function which lives on a circle, and you want to measure this, you want to estimate this, and every time every time you take a measurement, it gets rotated by some amount, by an unknown amount. So you can take as many measurements as you want. So the function will travel all over this circle. So if you take you can take as many measurements as you want, and you can take the average. What you will get in the end, as instead of this theta, is because of the rotations, you will just get a constant blur all over this circle. You are not going to recover the original function. So that's the fundamental conceptual difficulty, and it drives much of the complications which underlies the study of this model. So if there are any questions, please feel free to stop me and ask me. Yeah, so I will just state the model in the next slide. And okay. So let us frame this as a concrete model. So we want to understand some function or molecular density, or maybe just some signal or vector in R to the P. So theta star is a true signal. And our observations consist of the following. These are yi. There are n observations. Each yi consists of two components. First of all, there is a noise xi, which is additive and generally thought of as Gaussian. And then you take your true signal or true vector and you multiply it by GI, which is a rotation. So OP is the orthogonal group on acting on RP, and GI need not be the full orthogonal group. Maybe the GIs just belong to some subgroup of the orthogonal group, and I will come to some natural examples very soon. And for modeling purposes, we just, since we have no control on these GIs, we just, and often they are of random origin, so we just assume that the GIs are IID uniform according to Haar measure on some compact subgroup of orthogonal. And the XIIs are usually IID standard Gaussians with mean 0 and variance sigma square in dimension p. And the first observation is that with the observations of this nature, there is no hope of really recovering the true theta star because all we are observing are some rotated versions of theta star. So we can only recover theta star up to its orbit under the action of G. So instead of asking for theta star, the natural question to ask is to ask for the orbit of theta star under the action of G, which we will denote by O theta star. And this object will keep appearing again and again. Okay, so what are some examples? So the first very simple example is learning a bag of numbers. So suppose I have a set of numbers which whose ordering I do not care about, but this set of numbers are nonetheless laid out as a vector, and I can take many measurements of these numbers, but at every measurement they get permuted in a random way according to a uniform random permutation. And the question is, what are these numbers? Okay. So if you think of it, the orbit consists of exactly all the vectors whose coordinates in some order is our bag of numbers of interest. So here is another example. Learning a rigid body. So what is a rigid body? So one natural way to think of a rigid body is that, so suppose there are n particles which comprise the rigid body, and they are in k-dimensional space. So each of these n particles are each of these n particles is represented by a vector in r to the k, and you can then line up these n particles as columns in k-dimensional space and get n cross k or k cross n matrix. And basically the way a rotation acts is that the same orthogonal matrix of the same rotation must act on all of these columns. So the natural way to pose this problem is to just multiply this by a matrix which is in the orthogonal group in k dimensions. Okay. So the third example is that of multi-reference alignment. So this is a particular this is a reasonably simple example because the G the group of isometries here is an abelian group. It is Z mod PZ, and the way it works, the way to visualize it is exactly this picture that we drew here. So imagine that instead of the continuous circle, this is some sort of discrete circle. So this is some representation of this is some visualization of Z mod PZ. So there are P coordinates here, and you can think of your theta star, your vector, as a function from these coordinates, these markers to the real number, and every time you observe it, your function gets rotated on the circle by some amount. Okay, so this is multi-reference alignment, and your group of isometries is the group of cyclic shifts on the coordinates of RP. And then you can talk about the spherical registration problem. So this is, in some sense, this is the continuous and three-dimensional version of the MRA problem. So you have a function which continuous function which lives on the sphere S2, and then the group is let's say the group of rotations in 3 dimensions, and it acts on the function space as in the form of the left regular action. This is not exactly so far all the other examples we have been discussing are discrete examples, whereas this is a continuous one. But there is a way to discretize this, because you can go to the Fourier side, on the non-commutative Fourier basis for functions on S2, and there you can approximate f by in some sense a discrete series, and then it will become a discrete problem, and the SO3 will act in a natural way there. So in some sense, so this problem, the spherical registration problem, also falls within the ambit of these questions that we are discussing. Okay. So there are other variants of cryo electron microscopy. So this model that we discussed, quite, on the face of it, it's quite simple. So you can add some bells and whistles to this, and you can make it more sort of make it correspond in a more close manner to the reality of how you may take images. So for example, you can add a linear mapping on your rotated objects. And this is natural because if you think of taking an image in reality, it's usually a 2-dimensional image of a 3-dimensional object. So at some level, at some point, a linear projection onto a 2-dimensional plane is taking place, and this pi is this pi represents that linear projection. And then there are generally in lab experiments, the chemical molecules are usually not of a pure type, so not usually not of a single type, but usually it's a mixture, heterogeneous mixture of different types of molecules. So you can model that by making this theta star being a random choice from a finite set, and you want to understand what this set is. Okay, but today we are going to just focus on the basic model and see what the fundamental issues are which are imposed by the presence of this latent group action. Okay. So if you want to talk about recovery, then we have to define a metric or a distance, and this is the natural distance. So our θ1 is said to approximate θ2 well if its distance from the orbit of θ2 is small. Okay, so this is our notion of metric. And then just to lay the groundwork, so there are two possibilities here. So we can study generic signals versus worst case signals. So in terms of worst case signals, we want to prove recovery guarantee or a speed of convergence for all possible θ star. Whereas in terms of generic signals, we would be happy if we are able to demonstrate some rate of convergence which holds for all θ star except in a set of measure 0. Okay. So and this will be important because the worst case behavior in this model is significantly bad compared to the generic behavior. Okay, so what are the natural questions? So how to perform recovery? Excuse me. How to perform the recovery of the orbit of θ star? How many observations do I need in order to perform this recovery at a given accuracy level? So this is popularly referred to as sample complexity. And then we want to compare the sample complexity of our proposed procedure to the optimal sample complexity, which is how many observations are minimally needed to do this recovery. And usually this corresponds to so-called information theoretical lower bound in statistical problems. And then there is the question of computational complexity. So for example, how to perform this recovery fast, for example, in polynomial time. Is there a computational statistical gap in this model, and so on? Okay, so let us first take the basic first basic step, this is the method of synchronization. So synchronization is a natural approach to orbit recovery problem, and the idea is that if your model is yi equal to gi times theta plus ii. And the main problem is that this theta, these gi are unknown. So if these gi's were known, then this would be a very simple problem, because then we would just multiply both sides by G inverse and then just do the usual statistical procedure on GI inverse YI, right, instead of YI. So the main idea in synchronization is to try to estimate the GIs, which we do not know, as well, try to estimate them as well as we can, and then try to use that to to invoke the usual statistical methods. So concretely, we attempt to find HI, which minimizes this discrepancy measure. So of course, there are computational challenges in doing this fast, but even otherwise, so suppose we are able to solve this sort of discrepancy minimization problem over this compact group G of orthogonal transformations. And then we can, as a candidate for our theta star, we can just take this HI, this GI inverse YI, which is HI hat here, HI hat inverse YI, and take their average, and that should do the trick. That should do the job. So that's the basic idea in synchronization method. But the problem is that synchronization works only in the low noise regime. And in fact, it has been proven that in the high noise regime, no consistent estimation of the GI is possible. And just to give you a cartoon explanation of why this can be the case, so you can imagine that the noise is really low and your signal is well separated from the noise on its support. Okay, so in that setting, the point is that to find these rotations, you do not need all the information on the y-axis. So for example, if you could understand what the support of your signal was, then already, or some high points of your signal, then already this would probably be enough to recover the GIs, because the rotations are, for example, fixed by only a small number of points. And in the low noise regime, this can be done with this can be done effectively or accurately. In the high noise regime, the level of the noise is so high that it is much, so the noise level, so for example, if this is normal 0 sigma square I, the noise level sigma square is usually taken to be much bigger than the norm of theta. So whatever information is contained in a single image is usually swamped out by the noise. So and in fact, in the theoretical literature in this topic, the popular or the important scenario is to keep all the other problem parameters fixed and send sigma to infinity. Okay. So synchronization is a natural, a canonical approach to this problem, but this works only in the low noise regime. So we are stuck. So since we are stuck, so let us for the moment briefly stop worrying about trying to solve the actual problem and estimate theta star or its orbit, and instead let us try to focus on what we can estimate. Now suppose I consider a function of theta or theta star, let's say. Suppose I consider a function of theta star that is invariant under these rotations. So I take my image, which is theta star, rotated version of theta star plus noise, and I just compute this functional of theta star or its GI of theta star, which is invariant under rotations. So if F is invariant under the action of this group G, then F of GI of theta star is equal to f of theta star, right? So if I was just looking at this kind of functions, then we are in relatively better shape, because the actual object, at least the expectation value, doesn't change from one observation to another. So for example, so let us give some examples. So for learning a bag of numbers, we can look at the classical moments. These do not depend on how you permute your coordinates. For the multi-reference alignment, where your group is cyclic shift and your vector lives on the discretized circle, you can still look at the classical moments, but you can also look at other quantities which are basically functions of pairs of consecutive coordinates, and these also do not change when you cyclically shift your vector theta. So for these, one can, because the actual observable, the true observable f of theta does not change from one rotation to another, you can hope to use the usual statistical methods and do averaging to estimate these well. So these are the functions. So these functions, this class of functions which are invariant under the action of the group G, can be estimated well using classical statistical methods. So these are some good functions, good for us in the context of this problem and this noise model. The question is, how far can it take us? In particular, can it take us all the way and help us find out the true theta star or its true orbit O of theta star? So this is this connects to the classical invariant theory of polynomials. So this is the theory of polynomials that are invariant under the action of a group. And here we have the photo of David Hilbert, not because he invented invariant theory, but he did some of the most fundamental works in invariant theory by the turn of the century, from the 19th century to the 20th. And many of the key objects in this field actually bear his name. So let us do a little digression to invariant theory. So we consider p-dimensional vectors, and when we think of our problem in algebraic terms, what we are going to do is that we are going to think of the coordinates of theta as variables. Okay, so you should think of these xi's as the coordinates of theta. And we want to understand what is the class of functions of theta that we can estimate well using these invariant functions. So of course the group G can act on the ring of polynomials. So for example, if it is a cyclic group, it will cyclically permute these xi's, and it will give rise to a new polynomial from the old one. And some of these polynomials will remain invariant under the action of G, some will not. So Rx super G denotes the ring of polynomials that are invariant under the action of the group G. And based on what we have discussed, these are the good polynomials which we hope to estimate well using classical statistical methods in spite of the group action. And let U be a subspace of invariant polynomials which we have access to. For example, U would be something like the classical moments that we have written down here for the bag of numbers example. And the question is, so suppose we are able to estimate well these good invariant polynomials, then are these enough to determine the orbit of theta star, or when are these enough to determine the orbit of theta star, if at all? Okay. This is the basic problem. Basic theorem in invariant theory tells us that the full invariant ring, so if you could estimate all invariant polynomials, this identifies theta for every theta in RP. And this is very fundamental because the point is that if even the full ring of invariant polynomials Rxg could not identify theta, then of course we do not have any hope to find out to estimate theta correctly based on the class of invariant polynomials that we can estimate, which is usually smaller. Okay. So this is like a fundamental existence theorem. And in order to study all these quantities, it is usually useful to consider the so-called Reynolds operator, which is essentially just averaging under the group action of G. Okay, this is the averaging operator, and in this area it is referred to as the Reynolds operator. So let us see a quick proof of why the invariant ring. Actually, maybe we should skip the proof because there is limited time left. But it is basically it's a classical, it's an elementary argument, and involving separation of points in a compact Hausdorff space and using the Reynolds operator. Okay, so let us take this theorem for granted, and let us move on to further concepts. So our basic question is, we understand that there is a class of nice polynomials which we can estimate well. The question is how far we can go from there, go using those. And in particular, we want to know at what point which polynomials would be good enough to just test. We do not want to test more than, we do not want to estimate more than we need to. And we have just seen that if we could estimate all invariant polynomials, then we would be home and dry. So this brings us to the notion of algebraic independence. So polynomials are algebraically independent if they do not exist a non-zero polynomial in such that this non-zero polynomial kills your candidates. Okay, so this is the polynomial or algebraic version of independence, which is linear independence in vector spaces. So this is just the algebraic or polynomial version of that. And when you have a subspace, the transcendence degree of that subspace is just the maximum possible size of such an algebraically independent subset of U. So the basic idea is as follows. So suppose we were doing just vector space approximation, then we would be using just linear dimensions here instead of the vector space. The idea is that here we are considering polynomials in the coordinates of theta. So we should use a notion of approximation or spanning by polynomials in your basic observable. So think of the subspace U to be a linear subspace of polynomials that we can estimate well using these procedures. And then the question is that by how many of those are sufficient to determine the space of all polynomial functions which is generated by your basic objects in U. So intuitively, so notice that if you think of the invariant ring of invariant polynomials, then then these invariant polynomials, they are all constants on an orbit. So you can, for any given orbit, if I give you a bunch of invariant polynomials, they will just be constants on this orbit, and therefore they just provide you with a bunch of fixed numbers which characterize that orbit. And from the characterization theorem that the Rxg identifies the orbit O theta for every theta, that means that if I knew all these constant values of the Rxg on that orbit, I would know the orbit. Okay, so in some sense, the values of invariant polynomials in an orbit form a coordinate system in that orbit, and there can be redundancies there because you could express one polynomial as a function of another, and the transcendence degree of Rxg is basically the minimal number of such parameters, such invariant parameters you need to describe this orbit. Okay. So if G is a finite group, for example, transcendence degree is equal to the dimension of the vector space, which is P. And if G is actually continuous, then this can even be smaller than P. In general, smaller this transcendence degree, the better for us, because that means that our orbit can be estimated by lesser number of parameters, which we know, which reduces the statistical and computational load of the problem. So here is a basic theorem. It's pretty recent. So it shows. So basically, the criterion for identifying a generic signal. So here the difference between genericity and worst case signal, generic signal versus worst case signal is important. And this theorem holds only for a generic signal. So if your signal theta star is generic, then your good subspace, which you can easily estimate here, will be as good as the full ring of invariant polynomials, and therefore identify theta star if the transcendence degree of what you have estimated is equal to the transcendence degree of the full ring of. So for example, if G is a finite group, you would in general need P, okay? Your transcendence degree should be P. And the converse is also true, but that is a bit less relevant for our purposes here. And given any finite dimensional subspace, there is an efficient algorithm to compute transcendence degree of that subspace. And by efficient, we mean polynomial time, and essentially this is a variant of the greedy algorithm, which works here. For more algorithms in type, you can of this type, you can look at Bernd-Stromfeld's book on algorithmic invariant theory. Let me introduce the last character in this story, which is the moment tensor. So the kth order moment tensor is defined as this object. So you can imagine it for k equal to 2. So if the G was not there, it would be just the matrix whose ijth entry would be theta I, theta j. Okay. And then because of the action of G, theta gets shifted, and then you just, for example, if G was finite, you just average it over G theta I, G theta j. Okay. And this is a matrix like this. This is for 2 dimension, for k equal to 2. In general, you can consider higher order tensors. And in this theory, actually, it is important to consider higher order tensors because k equal to 2 is generally not enough. And that's fundamentally due to the presence of the latent reflection. And as you can see already here, each entry of your moment tensor is a polynomial is an invariant polynomial, of course, because you are averaging over the group here. And each entry is an invariant polynomial that is also homogeneous of degree k. So this follows from the definition. Basically, you can see it here for k equal to 2. And it's nice that actually these moment tensors cover all the information that you can extract for when you are considering homogeneous polynomial, when you are considering invariant polynomials which are homogeneous of degree k. And in fact, any invariant polynomial that is homogeneous of degree k is linear combination of the entries of these moment tensors. So these moment tensors are quite fundamental. Any invariant polynomial you can decompose as a sum of homogeneous invariant polynomials of different degrees, and therefore by looking at the various kth order moment tensors, you should be able to get a good idea of what your invariant polynomial is. So because this is so important, because this is so informative, so we can try to think of how to estimate this. So this you can estimate by just replacing this quantity by your observations. So you take yi to the tensor power k, and you just take the average. And if k was 1, then this would be the mean, and you would actually estimate the average of the entries of theta. For k greater than equal to 2, there can be some bias terms, because y is there is this additive noise, and if you multiply them like tensors, there would be diagonal terms where the same xi gets multiplied, so we would get as xi square. So its expectation will be non-zero. So you have to correct for those bias terms, but these are easy to do. And you can look at all the for any k, you can look at all the signals whose first k moment tensors match, and clearly it contains, because the moment tensors are invariant under the action of g, therefore this moment tensor for theta is constant. It has the same value all over the orbit of theta. So if you look at all the all the signals whose first k moment tensors match, then of course the orbit of theta would be contained in its entirety inside this level set. And actually for k large enough, so imagine increasing k. So for k equal to 1, it's just your first order moment tensor is just the average and of the coordinates of theta, and there will be many vectors which tau with the same average coordinates, average of coordinates. Now, as you increase k, your constraints are increasing. So this set m theta star k, whose first k moment tensors match with your desired theta star, this m theta star k, this set decreases as you increase k, and it always contains orbit of theta star, and it is decreasing, and at finite, after some large enough but finite k, this will just collapse to the orbit of theta star. Okay, and actually if I give you a k, there is a very explicit estimator which is defined in terms of Hermite polynomials, which recovers approximately your moment tensor, your level set at the level k, up to an epsilon error. Okay, up to an epsilon error tolerance. And it can be shown that the number of measurements for which you need to do it well to beat the noise is the sample complexity has to go faster than sigma to the 2d, and this d should be k. I'm sorry, sigma to the 2k, and the reason why this sigma to the basic reason why this sigma to the 2k comes is because of these kind of product terms. So basically, if you take the kth order moment tensor, then noise will be multiplied with itself k times, and you should get its variance should be of the order sigma to the 2k. And roughly speaking, your n should be large enough to beat that. Okay. So let me. I have only 5 minutes left, so let me wrap this up by putting everything together. So how are we? So suppose we are given observations y1, y2, yn. How are we going to put all the information that we have discussed today and try to get a good handle on the orbit of theta star? So first, what we do is that, so first we need to know how many, so what is our target? So how many parameters do we really need to estimate? So this is the transcendence degree of the ring of G invariant polynomials, and here the observations do not enter. So this is like a deterministic algebraic problem, and this involves standard techniques which depend on the compact group G. Once we have computed the transcendence degree, now we want to start with some nice polynomials which we can easily estimate, nice invariant polynomials which we can estimate well, and try to keep increasing this bucket of nice invariant polynomials which we can estimate well until its transcendence degree matches the transcendence degree of the true invariant ring. So we start from j equal to 1. And our nice polynomials will be exactly this moment, the entries of these. It will be our nice polynomials will be the entries of these kth order moment tensors or jth order moment tensors. So we start with one. The first order moment tensor is just the sum of the average of the entries of your x or your theta, and then we increase the order of the moment tensors. So this increases the size of your spanning set U, and we keep an eye on the transcendence degree of U, for which there is an efficient algorithm to compute the transcendence degree of a finite subspace. And then, and this transcendence degree is in general increasing as we are increasing the degree or the order of the moment tensor. And at some point, and at every step, we check if the transcendence degree is already of U at our given degree J is already at our given level J is already it already covers enough parameters to estimate the function. If not, if yes, we stop. If not, we go to the next higher order of moment tensor and repeat and keep repeating until this criterion is matched. So when this criterion is matched, so let's say it when this criterion is satisfied. So let's say it happens at degree k. So we have kth order moment tensors and everything below it, and the transcendence degree of the linear subspace generated by those is equal to the transcendence degree of the full invariant. That means that by using these k moment tensors, we have reached a stage where we have enough information, we have enough parameters to estimate the full orbit of theta star. So far data has not entered. We are just dealing with the group. So for this K, now we go back to the result of this recovery algorithm, this sub-level set recovery algorithm of the previous slide, and use that algorithm. So this depends on the data. We estimate m theta star k up to accuracy epsilon via the estimator which was discussed in the previous slide, and by the choice of k, this is roughly okay. I am hiding some technical complications here, but roughly this should be the order of theta star. So roughly speaking, or approximately, this m theta star k, which we estimate up to an accuracy epsilon, should also identify the orbit up to some ambiguities. Okay. Yeah. So I am almost at the end of today's talk. So, but there is more extensive studies can be done on this model of learning under group invariance from a stochastic modeling point of view. So you can study the likelihood landscape of the orbit recovery problem. And Gerard Benarus was supposed to be here, but unfortunately he could not be with us here. So if he generally is very fond of this kind of likelihood landscape investigations. And then you can study the information geometry of the Kullback-Leibler divergence on these probability models. So if I take the true theta star and if I take another alternative theta, which is close to theta star but not exactly the same, then how does the Kullback-Leibler divergence behave, particularly in the neighborhood of theta star? So interestingly, it admits formal expansion in a series in sigma inverse in the high noise regime, which is of interest to us. And this series, this formal series, the entries of this formal series, the coefficients of this formal series actually depend on the crucially in an intricate way on the ring of invariant polynomials, particularly these moment tensors. And there is a detailed spectral structure of the Fisher information matrix, again, which can be very accurately described in terms of the G invariant polynomials in the coordinates of theta. And then one can, there is recent investigation on specific models which are of greatest interest. So, for example, the multi-reference alignment model, where the group of isometries is the cyclic group, but with structural constraints on the signal. For example, when your signal is sparse, which corresponds to a more realistic scenario, and it connects to Fourier analysis, phase retrieval, and various techniques from combinatorial optimization. and maybe we will have the chance to cover some of these topics in the last lecture. But let me stop here today. And here is a list of references where you can take a look at this, and let me know if you have any questions.